Good morning, students. So, good morning, students. Last class we discussed about the what is the concept of corona and how corona will be occurred in the overhead transmission line, and what are the factors affecting the corona, and what are the advantage disadvantage of corona. What is the some technical terms, that is critical descriptive voltage and visual critical voltage, corona loss, that is power loss, were all discussed in the last class. Now we go for the another topic, that is SAG, mechanical design in transmission lines. SAG in overhead transmission lines. A straight distance between the two poles. That means two poles are, the conductor is in between two poles. That may be given a short distance. Therefore, to minimize the length of the conductor, one may stretch conductor to make it straight. But we also look after the conductors are in safe tension in order to permit safe tension the conductors. That means it does not fully stretched, but they are allowed to have some dip. So exactly two conductors, I mean two in between two poles, the conductors are stretched straightly, but because of some tension, to permit safe tension, we have to give some dip only. Dip means lowered. So thus the difference in level points of supporters and lowest point on the conductor is called sag. So sag is nothing but the difference between level points of supporters and the lowest point on the conductor is called sag. Look at the figure. Generally, so this is the straight. So these are the two poles, span between the two poles, and the conductor is in straightly connected. Because of we have to provide some provision to the conductor. That means we have to provide some tension, safe tension to the conductor. That's why we have to give you some dip. This is the dip. This is the dip. That means the conductor is in connected is in between two poles having some dip only. So now the difference between original level of the conductor to actual level of the conductor, this is nothing but sag. So these are the insulators like this. So tension tower, supporting tower, span between the two towers, right? So look at the figure. So this is the AB is the, suppose you can consider as AB is a straight conductor. Because of we are giving some safe tension to the conductor, we have to give some dip of the conductor. That's why the conductor will be like this. Now original position of the conductor is AOB, general AB. Now the difference between AB, length between the AB and AOB is nothing but sag, like this. When the conductor is suspended between two supporters, I mean two poles at the same level, it will take shape of catenary curve. So very important bit. What is the shape of sag? Otherwise, what is the shape of conductor suspended between two poles is nothing but catenary curve. However, the sag is very small compared to the with span. The sag span curve is like parabola. That means sag is very low. Look at the figure 2. So here this is the catenary curve. Figure 1 will gives the catenary curve. Figure 2 gives the parabola. That means the sag is very low. At that time the sag curve is parabola. The tension at any point on the conductor acts as a tangentially. So tangential, that means tension at any point like this, it will act as a parallel, that is nothing but parallel to the conductor. So this one, it will act as tangential force. tension will act as a at any point. That means conductor may acts tangentially. Thus the tension T naught at lowest point O act as horizontally as shown in figure 2. The horizontal component of tension is constant throughout the length of the wire. Horizontal does not change, only vertical length will be changed. So that is nothing but vertical difference. Exact difference between sag is nothing but the difference between the vertical length of the original conductor and actual conductor. The tension at supports is approximately equal to the horizontal tension acting at any point on the wire. Thus, if capital T is the tension at supporter B, then T is equal to T naught. So look at the figure. This is the quaternary curve. A and B are the supporters, and the length is L. Now, to take in a midpoint, that is O. Now the length is divided into L by 2, L by 2. Now I am taking at particular point P, right? So let us consider conductor between two equal supporters A and B with O as the lowest point. It can be proved that lowest point will be at the midspan. Small L, length of the span, W, weight of the conductor, T, tension of the conductor. Now let us consider a point P on the conductor. Now taking a lowest point O on the origin, let coordinates of point P will be X and Y. We are taking coordinates. So X is the this coordinate and Y is this coordinate. Assuming that curvature is very so small, that curved length is equal to its horizontal projection. So this length is very equal to horizontal projection. That is OP is equal to X. Approximately we have to take in OP is equal to X. The two forces acting on the portion OP of the conductor are, two forces are acting, that is weight Wx. So this type force, vertical force, that is the Wx at a distance of x by 2, right, from the O. It will be acting a vertical force, that is value of vertical force is Wx with a distance of x by 2, where from midspan, that is O. Next, second force, horizontal force, that is nothing but tension. It is acting at O, horizontally taking tension, that is also for two forces, vertical force, that is the Wx, and horizontal force, that is the tension. That means we have to calculate the sag value. Suppose two supporters are equal level, two poles are equal levels. At that time, span is high. We have to calculate the sag value, derivation. So equating the moments of two forces at equilibrium point or midpoint, that is O, we are getting Wx multiplied by x by 2 distance, T, tension, with a coordinate y. So Ty is equal to Wx into x by 2. Therefore y is equal to Wx square by 2t. Now the sag is nothing but maximum dip or difference between the two levels, right? I mean original conductor level and actual conductor level. Maximum dip is represented by the value of y. Look at the figure. Dip is nothing but this is the y. We have to take in point P. That's why a small point P will take in. That's why y is the maximum dip. Now y is represented as the value of maximum dip in between A and B supporters. Suppose I am taking from support A, x is equal to what is the length between A to O, that is L by 2, right? So x is equal to L by 2 and y is equal to S sag, right? Substitute the x is equal to L by 2 and y is equal to S in the above equation. So therefore sag is equal to S is equal to W into x means L by 2 square by 2t, that is equal to WL square by 8t. So very important formula for competition examination, and any type of examinations. Sag at equal level of supporters. At equal level of supporters, the maximum dip or sag is nothing but WL square by 80, where W is the weight of the conductor, L is the length of the conductor, T is the tension, right? Suppose next case, when supporters are at unequal levels, poles are not equal. If poles are equal, already you have to derive the sag formula. S is equal to omega L square by 80. Now coming to the second case, that is when supporters are at unequal levels. B having more than the A, otherwise A has more than B. That is nothing but both are not equal levels, so both are in unequal levels, both are at unequal levels. So let us discuss this how can you derive the sag from this scenario. Generally equal levels are not considered in hilly areas, right? That means in hilly areas, so the levels are not equal. So always levels are unequal. That's why we can consider in hilly areas, we can derive the sag, how the sag will be affected by the at unequal levels. We generally comes across the conductor suspended between two supporters at unequal levels as shown in figure. B has height, B has more level compared to the A. Now the figure shows a conductor suspended between two supporters A and B, which are at different levels. The lowest point on the conductor, as usual, O, we can consider. So lowest point or maximum dip on the conductor is nothing but we can consider O. Let us consider L is the length of the conductor or span length, H, difference in levels between two supporters. That means, so how much differ from the A? That means pole B having how much differ from A? Pole A is nothing but height of the supporters. Difference in levels between two supporters. X1 distance of support at lower level. So this is the X1. From OX2 is a distance. Now if W is the weight for unit length of the conductor, then sag S1 as usual omega x1 square by 2t, sag S2 omega x2 square by 2t. In general, if x is equal to L by 2, we are getting equal levels. S is equal to omega L square by 80, right? But here the case is different, the scenario is different. Both are different levels. That means we know the total length L. That's why from A point to midpoint we can consider X1. From midpoint to B supporter we can consider X2. That's why sag S1 omega x1 square by 2t, sag S2 omega x2 square by 2t, right? Now what is the x1 plus x2? Complete length L. X1 plus x2 is equal to complete length L. But in former case, x is equal to L by 2. Equal levels means L by 2, L by 2. That is nothing but L by 2 plus L by 2 is equal to L. So like that, for different levels, x1 plus x2 is equal to L. So now we know the S1, we know S2, therefore difference between S2 minus S1 omega by 2t x2 square minus x1 square, then A square minus B square, A minus B, A plus B, right? Omega by 2t x2 plus x1 into x2 minus x1. We know the x1 plus x2 value, that is L, omega L by 2t x2 minus x1, right? Omega L by 2t x2 minus x1. What is the x2 minus? Generally, what is the S2 minus S1? That is nothing but H. So difference in level is nothing but H. So H is equal to omega L by 2T x2 minus x1. Therefore, x2 minus x1 is equal to 2TH by omega L, taken as equation 2. So we know the equation 1, that is x1 plus x2 is equal to L, right? Now we know the x1 plus x2 is equal to L. We know the x2 minus x1 is equal to 2TH by omega L. Now solving equation 1 and 2, by adding these two, x1 cancel, 2x2 is equal to, right? So some equation will be coming, and from that equation we have to determine x1 also. So lastly we have to determine x1 is equal to L by 2 minus TH by omega L, x2 is equal to L by 2 plus TH by omega L. By having x1, x2 values, we have to find out the s1, s2 easily, right? So now what is the factor of safety? Generally, to account for unforced loads, we take working tension, Fs, or ultimate or maximum strength by working tension. That is nothing but factor of safety is defined as the ratio of ultimate strength or maximum strength divided by tension. So suppose what is the main drawback of loose span? So the conductor between two supporters having more dip. Permissible dip, there is no problem. Suppose more dip, what is the problem? Weight sag increased. So weight increases, when our weight increases, sag is also increased. Why? Because sag is equal to omega L square by 80. Short circuit between conductors may occur. Why? Because it may be touching to each other by the wind stream. When wind stream comes, so both conductors are touching to each other. That means, so there may be chances to short circuit occurs between two conductors. Breaking of conductor at any point of fixing may occur. So conductor may be broken. Height of towers have to be improved to provide ground clearance, right? So what are the factors affecting the sag is nothing but S is equal to omega L square by 80, where omega is nothing but weight of the conductor and T is the tension, L is length. Apart from these three parameters, so the sag is also affected on temperature also. What is meant by stringing chart? Stringing chart is basically it is a graph drawn between the sag and temperature, sag versus temperature, and also tension versus temperature. That means two graphs, one is drawn between sag versus temperature, one is drawn between tension versus temperature. That means a string chart is a graph drawn between tension comma sag with variation of temperature. That means what is the main use of this stringing chart? This is very important for competition exam. Stringing chart is used for, or stringing chart is drawn between which parameter, like that. Stringing chart is useful to knowing the sag, to know about the how much sag is available between two supporters, and also tension for weather conditions. If temperature is high or temperature is low, what is meant by sag and what is meant by tension. Stringing chart gives the data for sag to be allowed and the tension to be allowed for a particular temperature. That means mainly utilized to calculating the sag values and the tension values on a particular conductor under worst conditions such as maximum wind pressure and minimum temperature by assuming the suitable factor of safety. Mainly why the stringing chart is mainly useful is nothing but, first of all, to find out the sag on the conductor, sag in the conductor, then tension also, then insulator design and design of tower also, and distance between the two towers also. Generally, we have to derive the sag calculation at equal level of supporters, unequal level of supporters. Then, if suppose wind effect is there, what will happen? Ice effect will be there. What will happen in between two conductors? So that is the another derivation. Three cases. First case, equal distance, equal level, not equal distance. Equal level of supporters, S is equal to omega L square by 80. Unequal level of supporters. Right, we have to determine the x1, x2, substitute x1, x2 values in S. You have to find out the sag values. Now, if ice and wind effect is there, what will happen? The above formula for sag are true only in still air and normal temperature. When the conductor is acted by weight only, that means in normal temperature, the conductor is mainly acted on its weight only. If in actual practice, conductor may have ice coating and simultaneously subjected to the weight of ice act always vertical to downwards in the same direction as weight of the conductor. The force due to wind assumed act as horizontal, so in the same as tension. That means already we discussed tension force will acting on the horizontal and weight force will be acting on the vertical. Similarly, so the wind pressure, the weight of ice acting on the downwards as same as weight of the conductor, and force due to wind will be acting on the same as tension force. Now the total force on the conductor is the vector sum of the horizontal and vectorial forces. Look at the figure. So this is the vertical force. Already the weight is there. Now because of ice, extra weight is coming. Therefore W plus Wi, and this is the W that is nothing but wind. Now vector force of W plus W is nothing but W total. W total is equal to square root of W plus Wi whole square plus W square, where W is the weight of the conductor. So Wi weight of the ice for unit length, wind force for unit length. So we have to determine for following points also. The conductor sets itself in a plane angle theta vertical, where tan theta is equal to opposite by adjacent, that is W by W plus Wi. From this we have to determine the sag omega t total. Omega t means total, L square by 2t. Suppose we have to determine the vertical sag S cos theta also. From this we have to determine cos theta, and from this S, now we have to determine vertical sag. Very important for problematic. Sag template is used for allocation of the position of the weight of the supporters for different levels of the conductors. Hot curve, ground clearance curve, support foot curve. Hot curve is obtained from plotting the sag at a maximum temperature against span length. Ground clearance curve is below that hot curve, and support foot curve is locating the position of the supporters for tower lines. Sag for different range of lines, less than 66 kV, so it may be 20 feet. 66 to 110 kV, it may be 21 feet. 110 to 165 kV, 22 feet. Greater than 165 kV, we have to take in as 23 feet for the sag. What are the advantage of and disadvantage of sag? Sag determines the value of safe working tension, and that means it gives a minimum clearance of the conductor with respect to the ground. That means sag should be kept in minimum position in order to reduce the conductor material to avoid the extra pole height for sufficient clearance above the ground level. Suppose what is the disadvantage? Nothing but sag is very small. The tension between two supporters will increase. As tension increases, it leads to break down the conductors. So minimum clearance, kV and centimeter, I mean meters, 11 kV 5.5, ground in between the ground and conductor, 33 kV 6 meters, 66 kV 6.2 meters, 132 kV 6.2 meters, 220 kV 7 meters, 400 kV 8.4 meters. Like that, we have to providing a clearance between the ground and conductor. How to find out the spacing between the conductors is nothing but we have to provide an empirical formula S power 0.5 plus V by 150, where S is the sag in meters, V is the line voltage. This is the ground level and this is the minimum clearance. So sag at maximum electrical load, sag at maximum ice and wind load, final loading, installed loading, initial loading. Thank you. Next class we discuss about the problems on insulators, problems on corona, problems on sag. So third unit theory is completed. Now next class we discuss about the problems on third unit. Thank you.